In this video, we'll be dealing with what is molecular formula, what is empirical formula, how these two are interrelated, and on how to find molecular formula and empirical formula of a given compound. So let's begin with the definition. Now, molecular formula, I like to call this as the regular formula. The definition for this is the actual or regular formula which tells us about the number of atoms present in one molecule of a compound. So let us take some compounds that we already know. Now this compound is C6H12O6. This compound is known as glucose. So in one molecule of glucose, there are 6 atoms of carbon, 12 atoms of hydrogen and 6 atoms of oxygen. So if you see, this formula tells you about the actual number of atoms present in a compound. So this formula is known as the molecular formula of glucose. Now if you see carefully, 6 is a common divisor of the subscripts. If you can divide 6 by 6, you can divide 12 by 6, you can also divide 6 by 6. It is the greatest common divisor, GCD, or highest common factor as we call it, HCF. If we divide each subscript by 6, what we get is 6 ones are 6 ones are, 6 ones are 6 twos are 12, 6 ones are 6, 6 ones are 6. So we get CH2O1, C1H2O1. We do not usually write 1 as a subscript, we just leave it. So this is the most simplest form of glucose molecule, and this formula is what is known as empirical formula. It's the simplest ratio of number of atoms in one molecule of a compound. So let us take another example. C5H10. This is an organic compound, hydrocarbon, which is called as pentene. So if you see C5H10, this is the molecular formula. Now the subscripts tell us about the number of atoms of each element present in the molecule. So there are 5 atoms of carbon and 10 atoms of hydrogen. When we analyze this, we see that 5 is the greatest common divisor for both these subscripts. So when we divide the subscripts by 5, what we get is C1H2. This is the empirical formula of pentene. So we see that the empirical formula doesn't really tell us about how many atoms of each element are present in a compound. It doesn't even tell us the total number of atoms present in one molecule of a compound. If you take this formula C5H10, it literally tells us that there are 5 atoms of carbon and 10 atoms of hydrogen, and in one molecule of C5H10, that is pentene, there are 15 atoms altogether. But this doesn't tell us about any such thing. So empirical formula isn't usually preferred in writing the identity of compounds. So we usually use molecular formula because this is a more precise one. Another example that I'll take here is a compound whose molecular formula is C3N12. The name of the compound is cyanuric triazide. So again, in this compound, we know that there are 3 atoms of carbon and 12 atoms of nitrogen. Now we're supposed to find out if there is any number that divides both of these two elements, the subscripts of these two elements. Can any number divide 3 as well as 12? And that number should be the highest number possible. So the number that divides both of these is 3. So we divide the subscript of carbon by 3 and subscript of nitrogen also by 3. So what we get is 3 ones are 3, 3 ones are 3, 3 ones are 3, 3 fours are 12. We get C1N4. This is the empirical formula and this is the molecular formula. So to summarize, molecular formula is the more precise, more accurate and reliable formula of a compound, whereas empirical formula has more to do with ratio of number of atoms. It gives us the simplest ratio. It doesn't tell us about the number of atoms or the total number of atoms in a molecule. So although empirical formula has its own significance, molecular formula is preferred more in chemistry. Now, let us find the relationship between molecular formula and empirical formula. We will see, can we make an equation that includes both molecular formula and empirical formula? To do that, let us take an example. Let me take example of ethene, C2H4. Now let us find its empirical formula. The greatest common divisor for 2 and 4 is 2 itself. So we divide these both by 2. What we get is C1 and H2. This is the empirical formula. And this one is the molecular formula of ethene. Now let us find the molecular mass of ethene. Molecular mass is nothing but the total mass held by each element in a compound. So let us see. There are 2 atoms of carbon and the atomic mass of carbon is approximately 12. Plus, there are 4 atoms of hydrogen and the atomic mass of hydrogen is approximately 1. So when we simplify it further, we get 2 into 12, that is 24, plus 4 into 1, that is 4. Finally, 24 plus 4 is 28. So this is the molecular mass of ethene. Now let us find the empirical mass. So there is 1 atom of carbon and the atomic mass of carbon is 12. There are 2 atoms of hydrogen and the atomic mass of hydrogen is 1. So when we simplify it, we get 12 plus 2, or which is equals to 14. So to find the relationship between molecular formula and empirical formula, let us proceed in this way. So the molecular mass of ethene is 28. The empirical mass of ethene is 14. Now let us find the ratio of molecular mass to empirical mass. So the ratio of molecular mass to empirical mass will be equal to 28 divided by 14. On further simplification, we see that the ratio simplifies to 2. 14 ones are 14, 14 twos are 28. So molecular mass upon empirical mass gives us a constant. The constant for ethene is 2. Now this constant will differ from compound to compound, so let's just generally call the constant as n. So if we rewrite this equation, we get molecular mass is equals to n times empirical mass. So how we can use this equation is, if you know any of the 2 variables, you can find the third one. Most of the time we will be knowing molecular mass and empirical mass, and then we will get the constant n. Once we get the constant n, we multiply this constant to the subscripts of the empirical formula, and that will give us the molecular formula. For example, in ethene, the empirical formula is CH2. So when we multiply the n value here for ethene, n is equals to 2. So if we multiply 2 to the subscripts of ethene, we are going to get the molecular formula. So C1, so when you multiply 1 by 2, you're going to get C2, H, there's already 2, so 2 into 2 will be 4, C2H4. And we see that this is the molecular formula. So once we know the constant and the empirical formula, we can easily find molecular formula given that the molecular mass is known to us. Let us do the same thing for another compound that I had already given, C3N12, that is cyanuric triazide. So the molecular formula of cyanuric triazide is C3N12 itself. So let us find the molecular mass is equals to, there are 3 atoms of carbon and mass of each atom is 12, plus there are 12 atoms of nitrogen and mass of each atom is 14. When we simplify it further, we get 36 plus 12 into 14, that is 168. So when we add them together, we get 204. The empirical formula of C3N12 is CN4. Since 3 is the GCD, greatest common divisor, we divide 3 by 3 and also 12 by 3. We get C1N4. So the empirical mass is equals to, there is 1 atom of carbon and mass of each atom is 12, plus there are 4 atoms of nitrogen and mass of each atom is 14. When we simplify it further, we get 12 plus 56, which is equals to 68. Now again, if we consider our equation, N, that is the multiple constant, is equals to molecular mass upon empirical mass. When we input the value for molecular mass, that is 204, and the value for empirical mass, 204, and the value for empirical mass, that is 68, and divide it is equals to 3. So if you multiply 3 to the subscripts of empirical formula, you're going to get the molecular formula. Like C, there is 1 here, so C1 into 3 will be C3, N is 4, so 4 into 3 will be 12, N12. So C3N12 is the molecular formula. So this is how you first find the molecular mass, then find the empirical mass. You find the multiple constant and multiply this constant to the subscripts of the empirical formula to get the final molecular formula. We'll be solving some more such examples and problems in the next video.